So first, thanks to Victor and the others for bringing us here, and I've learned a lot on the various talks and the various discussions, also during running I had in the morning. And I would try to connect a little bit to what Anna Maria said about, how do you use correlations of looking into many-body systems, and we use it in a completely different setting, which will be the Sine-Gordon, the quantum Sine-Gordon model. And good. Maybe let's start the following. How do we do experiments in cold atoms? We usually take pictures. And in these pictures, if the pictures are, if you take the right detectors, you see every single atom on there. This is an experiment in time of flight, where you see every dot is a single atom, and that's a parametric oscillator where you have a 10 dB squeezed twin beam coming out there, and this is the ground. So you have this is the transverse excited state in a 1D system, and it's a transverse excited wave function momentum. These are the two ground states of the twin beams come out, and you see every dot is a single atom. And this is about 100 atoms here and 100 atoms here, and if you count them, it's plus minus 1. This is one type of, or you can do, these pictures are more famous because they appeared in a glossy journal, are, every single atom in here is in a lattice, but it's in situ. This is the same thing, basically done in momentum space. So what are these type of experiments? What do they measure? They basically measure single shot realization of a correlation function. And when very high order correlation function, these are 500 atoms. Now the question is that what information is in these type of measurements? And I think up to now we throw basically everything away. Yeah? And we only take very few things and look at pictures and count, where are atoms, or count how many atoms are here, how many atoms are there, and things like that. And there starts also to be theoretical ways how to calculate these type of things. Now, of course, if you want to try to evaluate a 500-point function out of that in a complete way, you will have no chance. It's just the computational complexity is way too hard to extract that. So usually what we do is we take, whatever, you do some kind of different unitary operator before you do your measurement. For example, that gives you an interference pattern, and from this interference pattern, you basically at each slice, you collect the phase, and this phase gives you the net, and because it's in a trap, it's a non-translation invariant correlation function, and you plot the G2 as a square, and the G2, this has 40 points in this direction, so the G2 has about 1,600 points in there, and it has the diagonal is 1 because the autocorrelation is equal to 1, and so you can get second order correlation function, you can get 4-point function, 6-point function, you get 10-point functions out, and this is just experimental data. So you can extract these things, but even the 6-point function, if you calculate it, completely has a terabyte. That also tells you how much information is in principle in these type of correlation functions, and it also tells you that this is going to be very hard to calculate and extract information out of these correlation functions. So what was our main motivation on this, on the thing that we did over the last years, was basically looking back at how did, one of the key things in quantum field theories was Schwinger's suggestion that basically, who said in these papers in the 50s, where he said, if you know all order correlation functions, they basically have solved the problem. Yeah? And then, of course, you think about it as an experimentalist. In the real world, I can only measure a finite number of these correlation functions. And usually, these correlation functions, they describe the propagation and scattering of excitations of the systems, or the modes in the systems in quantum field theory. And what does it mean to approximately solve the problem is basically to find the degrees of freedom where the correlations, where only the low order correlations really have relevant information. Yeah? If I find the degrees of freedom where the correlations factorize, I basically have to find the basis in which I can diagonalize my Hamiltonian. Yeah? So the question was, can we set out as a system which we can simulate, a quantum field theory, which we can simulate in an experiment, and test this type of conjectures and see what we can find out about this type of systems. And also in an experiment, this readout always has a finite accuracy and an error. And the question is that looking at these correlation functions and how they behave, and how much information is in any specific order of the correlation functions, I think tells you exactly how good your experiment is. I don't believe anybody who says he measures a very strongly correlated system who cannot show me connected correlation functions. Because if he cannot measure connected correlation functions, as we show you, he can diagonalize this Hamiltonian. Yeah? So I think this is a very way of really showing what is in the data, how can we extract it, and it's a way that to connect very beautifully to the theory of these many-body systems. So I will first talk a little bit about how in our very simple system, the quantum fields, the phases that we measure, and the excitations are related to the correlation functions, and then give an example, which is the quantum sine-Gordon model, where we basically quantify this factorization, verify that the model that we use, the implementation we use, is really described by the quantum sine-Gordon model, and then identify things like false vacuum states inside the model and something like that. And if I have time in the end, I can talk about a little bit about quantious and non-equilibrium physics that comes behind there. Let's see how far we get. So first, correlation functions. If I do a measurement, yeah, I usually, every measurement is connected to an operator. And if you as an experimentalist, if you talk to your theorist friends, you should always ask him, what is the measurement relevant to that operator that you calculate? Because then I can measure it. Yeah? So basically, an n-to-order correlation function is basically that quantity in average over the values of these operators at different points. Z, which just that can be any coordinate. For us, it will be position. Yeah. Now the question is that these correlation functions characterizes the propagation and interactions of degrees of freedom. They are connected to this operator O in the theory. Now, this on these correlation functions, there are whole libraries of statistical evaluations, and these correlation functions can be decomposed in something that's called the disconnected part of the correlation function and the connected part of the correlation functions. The disconnected part of the correlation function of order n contains everything that is fully determined by all the lower order correlation functions. So the disconnected part of the correlation function does not contain any new information. So any new information in the correlation function at order n is in this connected part of the correlation function. This really contains genuine new information about the system at order n. Yeah? And so if you cannot be able to calculate or extract a connected part of the correlation function at order n, means that you can describe your experimental data with perturbation theory up to order smaller than n. Yeah? Now, how do you do that? How do you get these things out? If I have let's say I take a correlation function of the phase, because we'll use this correlation function of the phase, and then you can calculate the connected part of the correlation functions from a sum over all possible partitions of lower order corrected functions, and that's a horrible way to evaluate. For example, in our experiment, if you want to calculate the connected part of a 10th order correlation function, we have to evaluate it way more than 10 to the 5 terms from our experimental data. That tells you how much complexity is even in a 10th order function, correlation function in there. Yeah? Of course, if the Wick decomposition is much easier to calculate because it only tells you what of this information of the nth order correlation function is still connected in the 2nd order correlation functions. And if you say that the Wick decomposition is basically valid, that tells you that I can factorize my correlation function, then harmonic, then I have then I can diagonalize my Hamiltonian. Yeah. So what do these connected parts of correlation function mean? I can make a very nice Mickey Mouse picture. It basically means that the 4th order connected part of a correlation function is the sum over all of the complete non-perturbative sum of all diagrams that have 2 legs coming in and 2 legs coming out. So in that sense, the 4th order connected correlation function is connected to genuine 2-body interaction. So that's simple. That's a phi to the 4th theory. Now, the sixth order connected correlation function is a sum over all terms that have 3 coming in and 3 coming out, or 2 coming in and 4 coming out, and things like this, which I cannot put together out of simple smaller vertices. So I cannot cut them apart and say, okay, first these 2 interact, and then these 2 interact, and these 2 interact. These 2 interact. Yeah? So, but these are basically the diagrams which I cannot, decompose in lower order diagrams. So this is genuine 3-body interactions. These are 3-body interactions which I cannot take apart anywhere else. And 8th order is genuine 4-body, 10th order is genuine 5-body. So these are pure quantum mechanical effects that come out because of all the different corrections, quantum mechanical corrections that come out of a simple 2-body interaction. So if I basically take a genuine Hamiltonian that has only 2-body interactions, quantum mechanics will give me all these other higher terms. And of course, if these terms don't get smaller, I'm in a strongly correlated system. So if these terms get smaller, I can write things down in a perturbation theory. So which system do we look at? There is the idea, the conjecture, and a beautiful calculation by Eugene and company that said that the 2 tunnel-coupled 1D superfluids can be mapped into the quantum Sine-Gordon model, and the quantum Sine-Gordon model is one of these very general quantum field theory models that, if you talk to somebody who comes not from solid-state physics, they say the quantum Sine-Gordon model is much more general than the Hubbard model. So the weakly interacting Bose gas, in some sense, we take bosons in the one-dimensional trap, and you have to confine them in such a way that they're really extremely strongly confined, so they have no transverse excitations. Then for the simple system, you have the exactly solvable Lieb-Lininger model, or has a low-energy effective theory, which is a Luttinger liquid, which would be a quadratic Hamiltonian. And if I now take a coupling into that, you add a non-trivial term in there where the cosine of the relative phase field phi is in there, and I can basically adjust the size of this non-trivial term by parameters that I have in it that I can dial in my experiment, which is the density, for example, and the tunneling rate, J. Yeah? And this term then gives you a lot of things, has topological excitations in the model and whatever you want. And of course, if this term is irrelevant, then it's a quadratic model. Or if this term is extremely strong, then I only see the quadratic part of the cosine, I have again a quadratic model. In between, I have a non-trivial model. So in an experiment, I can do it the following way. That would be the original Hamiltonian. Yeah, it doesn't look at all anything like the Sine-Gordon Hamiltonian. This is the original Hamiltonian with the 2-body interactions. And I can basically take a single, very elongated 1D system and split it. And in the regime where you have tunnel coupling, here you will have the Sine-Gordon model. Now, what goes in to take from that original Hamiltonian into the quantum Sine-Gordon model? And if you read the details, there's a following, there's a paper by Kritzev, Polkovnikov, and Demler in Fusor of B. They basically says you can separate the density and the phase. You expand the Hamiltonian in density fluctuations and phase gradients up to 2nd order and neglect all mixed terms. And then you can show that this Hamiltonian under these approximations is equivalent to the Sine-Gordon Hamiltonian. Now you see, you basically neglect all terms that are higher than 2nd order. And by measuring very high order correlation functions and connected parts, we can probe if this is good enough. And we can say if this is the real Sine-Gordon model that we can implement in the system. Why is the Sine-Gordon model interesting? It was one of the first models that showed in high energy physics a mass, the massive tearing model. And Sidney Coleman showed that the Sine-Gordon model is equivalent to the massive tearing model. The Sine-Gordon model is equivalent to the Coulomb gas. The Sine-Gordon model is equivalent to the XY model. And there are many, many things. There's whole libraries about what the Sine-Gordon model can do you. Now, it would be fun to see or to verify that the Sine-Gordon model is really something that I can implement in a quantum simulator with the tunnel-coupled 2 superfluids. So How do we do the experiment? One slide on how to do it. We do that on a chip because we can create very elongated one-dimensional gases that have temperature and density parameters about the same thing like Jeff told you yesterday. Very, very, very cold temperatures relative to interaction energy, very cold temperatures relative to trapping frequencies. And what is very nice on the chip, it's an extremely robust way to create a single one-dimensional system or a double one-dimensional system, and we can very beautifully measure the relative phase field, which is exactly that field which is in the quantum field in the St-Gordon model. We can measure that directly by measuring interference patterns. Now, from these interference patterns, say you have two superfluids that are tunnel coupled. You switch off the trap. In time of flight, you get an interference pattern. You take each of those slices here, and from that, you can basically extract the phase difference between the two condensates. And this phase difference between the condensates is exactly the field phi, which is in the St-Gordon model to be looked at. We can characterize the phase locking or the coupling of the two systems by this quantity average cosine phi, which is a coherence factor of the system, which can be directly mapped to these four factors in the St-Gordon model. So we can basically play around with that. And it also tells you, this average cosine phi tells you how much of the cosine potential of the phase phi my system sees. If average cosine phi is going to be very small, or is close to 1, it basically means that everything is located in the center of the cosine. I will only see the quadratic part. Yeah? And if it's basically 0, that basically means that I don't see the cosine at all. This will be the two limiting cases where the Hamiltonian should factorize. And in between, it will give me the systems. Good. Now, if I measure correlation functions, let me say a little bit about what usually you write down correlation functions of the fields like this, and then you can make if you then assume that the field operator can be written down as fluctuations of the phase and fluctuations of the density, and if you can neglect the density, then I could measure this correlation function by these e to the I phi Z1 minus Z2 correlators. Yeah? So if you measure these e to the I phi correlators and neglect density fluctuations, I would get the correlations of the field operators. And in fourth order, you can show that the same thing is, you just have to make a larger sum of that, and that correlator can be measured by that. And these are the phis, are these phases we get directly out of the interference patterns. Now there's a different way of measuring correlations with these phases, because if we want to measure phi is the field in my Hamiltonian, so it's better to measure direct correlations of the phase, phi of Z1 minus phi of Z2. So direct phase, not the e to the I phi correlators, but direct phi correlators. Note you have to unwind the 2 pi's of the phase. Yeah? The e to the I phi are easy to calculate because I don't have to care about the 2 pi's. Here I have to care about the 2 pi's. Yeah? But then you can show you can show that when you neglect the density fluctuations, you can show that these correlators are related to the creation annihilation operators of my excitations in the system. Yeah? So basically I have my quantum field, which would be without the excitations temperature t equals 0, and so basically measuring the phi correlators, you measure directly the excitations of the systems. Yeah? And again, you can show that the fourth order correlator is related to the interactions of the systems, and so on and so on. So we will use, because we want to see the physics of the excitations in the system, we will use these type of correlators, and not the e to the I phi correlators. And just a nice thing that the e to the I phi correlators, yeah, if quasi-particles interact, give a complete mess, because even the second order correlation function C2 already contains all order connected parts of the phi correlators. So if quasi-particles interact, this is a bad idea to look at in a many-body system. Yeah? Of course, in quantum optics, that's not a problem. Photons don't interact. That's why everybody uses these. Yeah? But in a many-body system, that's a bad idea. Because, you know, of course, if I have Gaussian fluctuations, it's not a problem. Then all of these things are 0. Yeah? Then these things give me everything. But if the fluctuations are non-Gaussian in my system, the e to the I phi correlators are a bad idea. So you have to really go back to measure the real thing. Now, let's see what we do in such an experiment. I take these interference patterns, get the phase, and now I give you a slice of this fourth order correlator, which is, 15 microns and minus 15. 2 points are fixed, which are 15 and minus 15 on the thing. And then, you plot, Z1 and Z2. And this correlator is symmetric because we picked this symmetric in such a way. Yeah? Now, if cosine phi is 0.01, basically means I have 2 completely independent latential liquids. That should be quadratic Hamiltonian. This is the full fourth order correlator that you measure. This is the fourth order correlator I calculate from the second order correlation functions. So this is the disconnected part of the correlation function. And if I subtract those two, I get the connected part of the correlation function that's 0. Which is nice, because it should be, if I have 2 latential liquids, 2 quadratic Hamiltonians, the connected part of the correlation function should be, the fluctuation should be Gaussian. Yeah? Now, if I take very strongly coupled system, yeah, here, cosine phi is 0.92. It basically means that, it sits down there in that cosine potential. It sits just down there where I can approximate it quadratically. Yeah? I see that the full fourth order correlator, the connected part, the disconnected part and the connected part drops out. Again, in that part, the Hamiltonian factorizes. Because I can approximate my cosine potential, my Sine-Gordon model, by the quadratic part.
But it's only should be one more to pi.
So, yeah. So we see that, yes. Now, this is, and then you can go here and look at, if you populate large fractions of the cosine, you see a significant connected part of the correlation function. Yeah? Now we can do that. This is basically a local measurement. We can basically know that, how important our interactions were. Of course, you can also do that and give an integrated measure. So you say you take the connected part of the correlation function and sum it over the whole fourth order correlation function and divide it by the full fourth order correlation function. So it tells you how important are the connected part in the fourth order correlation functions. If this is small, it means that most of the information is in lower order correlation functions. If this is in the order of 1, it means there's significant new information at order n in those correlation functions. And here you plot, for example, these are the measurements. Now, each of those measurements is something like 5,000 experiments. So people said that each thing is about 3 days. Yeah. So this plot has something like 100,000 experiments in there, and which have to run, day and night. So you see that here is that the complete sum over all correlation functions is very close to 0 here. It's very close to 0 here, and it becomes in order of 1 in between. Yeah? So that means that the interactions that are in the system are very, very important for the part. Now, to get to that, and this calculation, this band, is a calculation, for the Sine-Gordon model, there's a huge amount of literature and you can calculate these things directly, at least for thermal equilibrium. And this is a calculation for thermal equilibrium with exactly the measured parameters of our system. Now, what's the fast cooling? So slow cooling and fast cooling. Slow cooling is, to set this thing straight, slow cooling is that we have a typical collision rate of 10,000 collisions per second. Slow cooling for us is evaporative cooling throwing out about 2% of the atoms in 1 second, which is probably a factor 100 slower what everybody else calls slow cooling. Yeah? Fast cooling is throwing about 20% of the atoms out in 1 second, which means you throw 20% of the atoms out during you can do 10,000 collisions. Usually 3 collisions should be good enough to thermalize. It's not clear why, even at this relatively slow cooling, we see completely different sets of correlation functions. And especially what you see here is that you see that there's a huge connected part of the correlation function at very strong. Yeah.
Can you give the axial traffic period, because only then we can have a sense of what's fast and slow.
Look, the traffic,
axial, like, it might just be important to be slow because the axial traffic period is very slow.
Yeah, but the number of, usually, what should be axial? It's a local thermal equilibrium.
If I throw them out, then I have collective excitations in the gas, right? In the axial direction.
Okay, we can discuss about that later. I show you some data which contradicts that. Yeah? Because we have a different way of cooling in 1D systems where we can show which we can, if you just only look, so if you only look at the average quantities of energies and at the G2, we can cool the system significantly in 1 oscillation period. I mean, significant means by an order of magnitude in temperature, where it should officially not even be cooled. But I mean, this is a teaser which I can talk in the end. But yeah.
Yeah, so same Gordon model is integrable. So somehow one can suspect especially if you do fast cooling, it may not be even in the thermal state. Can you guys check if it's thermal or it's some?
How do we check it thermal? I mean, for me, I think that in the slow cooling state, and I will show you that up to 10th order connected parts of the correlation function, it looks like the thermal state of the St. Gordon model. This is for me the best evidence that is. No, only for the slow cooling. For the fast cooling, it just deviates. Yes, yeah, it's probably not the thermal state. Yes, but there's no theory I can compare it with.
Oh, but if it doesn't look like what we calculate for thermal state, then it's not the thermal.
Yeah, no, I know it's not the thermal state, but what it really is, I cannot tell you right now, up to now. Yeah. But what I will come back to you later on is that these are basically topological excitations that are frozen in the system from the cooling process, and I will show you that later. So you can do that for 6th order correlators, yeah, and I will do that. And of course, you can always compare it, the connected part of the correlation functions, and this is the Wick. This is the Wick decomposition, and this is the connected part of the correlation functions. So this is how would you see that the Wick decomposition? Of course, there's much more new information in there, but even if I take the difference between here and here, is basically the 4th order correlation function to take out. And then this is for the 8th order, and this is for the 10th order. Of course, the error bars become larger and larger and larger, and it becomes, really difficult to calculate that, because for the 10th order correlation function, I cannot store it anymore in my computer. It's too many points. It's 40 to the power of 10. Yeah? So I only have to get subsets from that. Yeah?
Sorry, may I ask, just to clarify, your connected is you subtract the products of the lower order correlation functions, yes?
Yes.
Which you've measured.
Measured, yes.
Measured, okay. So then what is Wick?
Wick is, I only subtract the 2nd order correlation function. Yeah? I said, what is, I only subtract the 2nd order correlation function. Now, correlation functions and full distribution functions have the same information. So if you take the full distribution function of your observable, or the correlation function of observable, in principle have the same thing. So we can look at the full distribution function of that observable, Yeah, and I think there are certain things that are much easier. This is usually completely ignored in which I think is bad, because I think it's a beautiful way of looking at things as full distribution functions. But so if you take the full distribution functions and you see that they're non-Gaussian full distribution functions, but they are in the end, when you get to the very low to very strong coupling, with very strong coupled one, it becomes very beautiful Gaussian. If I cool fast, I see that I have additional peaks in a full distribution function at plus minus 2 pi. What are these things at plus minus 2 pi? These are kinks. These are the topological excitations of the Sine-Gordon model. Yeah? And you see them directly in the experiment. If you look at the patterns, you can really pick them out. Yeah? And what it is as, what does it mean in the Sine-Gordon model, is that you have this potential of the phase. Yeah? If I plot phase phi, and then have here my potential, and maybe it looks like that. So usually, I would sit in here, yeah? But if I cool too fast, this is the same this is also a vacuum state. Yeah? And now if I sit in a vacuum state, if I sit in both of those things, I sit in a vacuum state as a high energy. It's a high energy which is given by that the field has to connect through there, and you see that the field connects through there by here. And that gives the vacuum of that system a higher energy. And that's why I think what you see here are basically, these are something like, the false vacuum states of Sidney-Coleman seen in a Sine-Gordon model. So I think that we can say that this correlation will help you identify the false vacuum states in the model, which you get if you cool too fast. Now, we can do an analysis which is pretty difficult, and I think this is just only hand-waving suggesting, is that we can try to look at the system, and if we know the full distribution functions, we basically take out these things. And then you can see we have, say, solitons and phonons have a very large connected correlation. Yeah. And then if I take out these solitons here, I see that the fluctuations in the system are Gaussian. Then you were somewhere here. Now, which is much more difficult is in the Demeter regime, you try to take out the solitons, which are very difficult to take out. So this is, and it's suggestive that even in that the connected part stays there, even if I take out the soliton, if we are in a regime where we should have also a connected part if we don't cool fast but cool very slow. So what have we learned? I think we can measure very high order correlation functions in the experiment, and I think I could have plotted you a 12th order and a 16th order function from the quality of the data, but I simply don't have the means of calculating them, or of calculating the error bars in them, if their statistically significant or not. Yeah, and also calculating some quantities, it just doesn't make sense anymore. You have to, it's there's just too much complexity in the system, or too much information in the system with the very high correlation. I think this full distribution functions and this connected part of the high order correlation functions contain genuine information about the quantum field theory I look at that. It contains information about the quasi-particles I look at that, about the modes I have there, about the interactions of these quasi-particles, and about the vacuum states you live in there. Yeah? And it gives an insight in effective theories describing the system. And as I said, in our 10th order connected correlation function is still significant. It basically means that terms up to 5th order have to be taken into account to describe the data. And also, it shows that this Sine-Gordon model, remember, this connected correlation function state for certain areas in the order of 1. Yeah? So basically means it's an extremely strongly correlated quantum system that you have in there. And you see it by the experiment. Yeah? And if you want to look at an experiment on strongly correlated systems, I think you have to be able to see these connected correlations. Otherwise, you're not sensitive to, in your experiment, to the physics of these type of things. Because then you can always say, I can describe my experimental data with a much simpler model. I think it tells you what is needed in the theory side to describe the data if you look at these correlation functions. Now, I think one of the key challenges, what I'm mostly interested in now, is that this is an extremely simple way of taking our data that we have and extracting something. To find, together with theory, a very general way for what information can I extract from a many-body system. And you have seen some beautiful examples from Anna Maria's talk. You know, there are different ways of getting at these type of experiments. And I think if we really want to learn more about many-body systems, I think we have to learn what are our measurements, how do we extract the data, and how do we connect it to what can be calculated in the theory. I don't know what's my time. Yeah, okay, so I can just show you one second thing, is that connected correlation functions die if you quantify into the free theory. They go away. Now, this is going to be an interesting way of looking at it. This is some very preliminary data in it. We have some simple models that allow, that seem to show how do these connected correlation functions go away. How does a system become Gaussian? After firstly being extremely strongly correlated, how does it become Gaussian after you quench into a Gaussian theory? And yes, so I think I can. And then we use correlation functions to measure recurrences of many-body systems of thousands of atoms, but maybe I can show you one single plot which shows that if you design your system correctly, long-range order comes back for a system with 5,000 particles, comes back once, twice, and if you look at the third time, and you can describe it in a beautiful way. But it's also interesting to see that the long-range order comes back, but the coherence factor does not come back, so it depends on which observer you use. You want to see quantum recurrences in a system. And this allows you to give a completely different insight into a quantum many-body system. Because this is, for example, how do these recurrences go down with temperature? And usually, this is basically the occurrences happen at a time when you already had a classical density matrix before. You know, you decay into a generalized Gibbs ensemble, and then long-range order comes back, and then it comes back, and then it comes back. So it gives you something tells you something about the underlying quantum physics that is underneath the system when it already looks classical in between. And what we clearly see from there is that there's physics beyond the latential liquid, in a latential liquid setting, and I think that gives you nice ways of doing it. So, good. So what have we learned? I think higher order correlation functions and full distribution functions, and especially the question how they factorize, gives insight into quantum many-body systems. It identifies interesting many-body quantum states, and detailed analysis of the correlation functions will give you much more insight. And we have observed quantum recurrences in a long-range order of an interaction-dominated system of 5,000 atoms. And the thing you can see, this is basically the same paper which was 2 years before in the archive. And this just came out there in the archive. And if somebody wants to read about the cooling, it's in there, but we can discuss over lunch. That would be an extra talk. So the experiments I showed you were done by Bernhard Rauer, Thomas Schweigler, Tim Langen, and Frederica, who is here. Where's here? Yes, she did the recurrence experiment part. And then, of course, there's lots of theory in there, and Sebastian, who did most of the theory for the St. Gordon, sits in front here. Good, thanks.